Okay, this is the topic which is impedance matching and the speed chart. Actually, I would like to show you the speed chart, and for showing the speed chart, we need this one because we have started the chapter 1. In the chapter 1, we have the speed chart. Let me show you. Standing wave ratio, the speed chart. This one, the speed transmission line chart. Okay, we have to look at this one. So before starting this one, let me show you the speed chart, a brief idea. Okay. That is our complete speed chart. If you look at the Google, then you can find it out. Okay, you can find out the speed chart. Just search the Google and write down in the search bar the speed chart. Then you'll get this one. Okay. So what we do using the speed chart? Actually, by using the speed chart, we do some calculations, transmission line calculations. We do the transmission line calculations by using speed chart. Okay. So see here, what we have found is we can find the speed chart. The rho means reflection coefficient. VSWR. We can also find out the VSWR using the reflection coefficient. We can find out the input impedance or the ZI using the speed chart. We can calculate the load impedance. Load impedance is known actually by using the speed chart. You can find out the load impedance, etc. Okay, well, you will see more of this. Okay, later. Okay, so we have to find out the speed chart. Okay, so before going to the tip, let me show you the speed chart here. That is the speed chart, and here the center of the speed chart 1. The center of the speed chart is 1. Okay, that is the 1, and this point is point of short circuit. This point known as the point of open circuit. This is the leftmost side is known as the PSC. That means point of short circuit, and rightmost line of the axis is known as the POC, point of open circuit. Okay, 2 point. PSC means point of short circuit, POC means point of open circuit. 2 point we have to consider here. Okay, so from here, from 1 to, if you go to the left, then it would be 0 here. And if from 1 you go to the right, then you will get infinity here. Okay, here is the infinity, here is the 0. Okay, so that is the thing. On the upper half, this is J X R plus Jx in the upper part. The lower part R minus Jx. So that is upper part and that is lower part. That means if you look at here, this is actually axis. Look at here. J omega, negative J omega. imaginary axis. Y is actually imaginary axis, and the X is actually real axis R. Okay, these axis you can write like this. Upper part inductive load, lower part capacitive load. Upper part you have to show the inductive load. Inductive load in the lower part you have to show the capacitive load. Upper part inductive load, lower part capacitive load. Okay. And then we have to look at here. Few more things you need to consider. See here. See in inductive reactance component or capacitive susceptance. So inductive reactance or the capacitive susceptance. And I have a call that you can this. Okay, sorry, I had a call. I had to receive a call. Whatever. So, uh, so that is our. If you look at the this line, this scale. Look at here. First scale is the wavelengths towards generator. The wavelengths towards generator. This is the first scale. Okay. This one consider the wavelength of generator. So, what is the wavelength towards generator? If you look at this one, this figure, that is a pitch of transmission line. We have to consider it. That is wavelength towards generator. Wavelength towards generator. WTG. That is WTG. Wavelength towards generator. And this is WTL. This wavelength towards load. Sorry, wavelength towards load. That is wavelength towards load, and that is wavelength towards generator. Two kind of things are there. Okay, towards generator and towards load. Now this one, if it started from here, then it is wavelength towards generator, and if it started from here to this side, then it is wavelength towards load. Okay, two things are there. Now, the thing is, wavelength towards load and wavelength towards generator. Okay. And look at here, this scale, angle of reflection coefficient. Third scale, angle of reflection coefficient, and final scale, fourth scale, which is angle of transmission coefficient. And here is the scale. There is another scale, which is the standing wave ratio and return loss. Some scales are there. You have to calculate those things. Now let me show you another. So now see the Smith transmission line chart. Many graphical aids for transmission line computations have been devised. Of these, the most generally useful has been one presented by P.H. Smith, which consists of the loci of constant resistance and reactance plotted on the polar diagram. Okay. Okay. Units radius corresponds to magnitude of reflection coefficient, and angle corresponds to phase of reflection coefficient. Refer to the general point along the line.
Hello.
Okay, you understand so far? That is, see, these things are the inductive load, and these are Capacity load. Okay. Now look at here, R plus Jx. R plus Jx. The complex variable W equal to the reflection coefficient. Okay, what about C? The pH speed transmission and calculator, 1939 and 1944. Here, long days ago. See, if one moves towards the air during increasing L, the angle of W becomes increasingly negative, which corresponds to clockwise motion about the chart. Motion toward the load corresponds to decreasing L and thus corresponds to counterclockwise about the chart. Okay. So these things, to find standing wave ratio and position of body maximum from a given impedance. Okay, we'll check this out using the example. Now, see impedance matching and Smith chart. So this is what? This is reflection coefficient actually. So if you minimize the reflection, then the maximize the transmission. If Z is below Z0, the line length is not important. If ZD is equal to ZC, generator impedance, maximum power to the load. We have to design matching so all Z's are the same. For matching the network, you have to the input impedance and the load impedance should be same. Okay, you have to put you have to measure the network in such a way so that input impedance and the capacity impedance become same. Okay. Now let's look at the Smith chart. That is our Smith chart. Impedance or admittance coordinate. Look at here. The green line, rho is equal to 1, which is the maximum reflection circle. See, we can generate the Smith chart line this way. This is known as the constant resistance circle. This circle is known as the constant resistance circle. Here R equal to 0 and A square plus B square is equal to 1. R equal to 0, R means the resistance is equal to 0. U and V, those are 1. Okay, R and X are normalized or real value. Okay. This is the constant resistance cycle. And this is the constant reactance circle. See, reactance circle. This is the reactance X. Sometimes X may be inductive XL or X may be XC. For XC, it would be negative. For XL, for the XL, it is positive, and for the XC it is negative. Now see, this is constant VSWR circle. These circles are the constant VSWR circle. So three kind of circles are there. Okay, first one, constant resistance circle. Second one, constant reactance circle. The final one, constant VSWR circle. We have three kind of circles are there. Okay, so let me show you the example. Okay, so that is example. That is circle. Now see, the example is here. So the load impedance is given, which is 50 plus J25 ohm. Load impedance is given, which is 50 plus J25 ohm, and this is the characteristic impedance, which is 50 ohm, That means Z0 is 50 ohm and ZL is this one. So first of all, what we have to do? We have to do one thing. That is, we have to find out the normalized value of the ZL. Normalized value. To find out the normalized value, what we will do? We will divide the ZL by the Z0. We'll divide the ZL by the Z0. Then what will happen? 50 divided by 50 plus J25 divided by 50. Then what you will get? 1 plus J of 0.5. Okay, so that is your normalized load impedance. That is your normalized load impedance. Now you have to put this value on the Smith chart. You have to put this one on the Smith chart. How to put the ZL? 1 plus J5. See, the first thing 1. That means this circle. R. 1 means R. R. That means the 1. The value of the R is 1. So this circle, you will consider this resistance circle, constant resistance circle. R. So this one. Then ZL. ZL is 0.5. So ZL, that means the inductance. Reactance circle, that is the inductance. Inductive reactance. Inductive reactance, that is 0.5. So 0.5 will be here. So your 0.5 here. This one is the next circle. Okay. Now that is your intersection point. That is your intersection point. Okay. That is your intersection point. So from here to here. That is your intersection point. So you have to find out the intersection point, which is the ZL. Okay, like this way. Now second part, how to find out the VSWR. Just join the center with the intersection point. Then you get a VSWR. That is the row. Sorry, this is the row reflection coefficient. And what is the VSWR value? See here. From here, you will get the VSWR as well as the reflection coefficient value. From the scale here. See, there is a scale. From this scale, you get the VSWR. Just calculate the length of that portion. Then you get the value of VSWR from the first scale. First scale, you will get the VSWR, and the last scale, you will get the row reflection coefficient value by using this method. Then, if you want to find out the phase of the row or phase of the reflection coefficient, then what you have to do? You have to just join. You have to just join this one. Join these two. and enhance it up to the circular scale. You have to enhance this line up to the circular scale outside perimeter, on the perimeter of the Smith chart. Then you will get the angle of reflection coefficient. Look at here. The angle of reflection coefficient is 76 degree. Okay, from this scale you will get a 76 degree. Okay, so that up to this, do you have any objection? Then you'll find out the value of the rho. In the previous one, it is 0.24, angle is 76 degree. Now you can write the reflection coefficient. Reflection coefficient is 0.24, angle 76 degree. That is your reflection coefficient value. Angle of reflection coefficient. Okay. Okay, so far you get it? Are you there with me? Guys, you understand?
Yes, sir.
Okay, so you have to download the Smith chart and print it. Okay, go to the, or if you have the printer, just print it out, several copies. Try to do it by yourself. Okay, because otherwise you would not understand how to use this Smith chart. That is actually practical thing. Okay, now see another one. Move along transmission line. So if you want, let's say, let's say 0.1 lambda along the constant VSWR circle. So if you want to move the line 0.1 lambda from the load to the generator, then what will happen? How will you find out the input impedance? So for this one, just calculate the first scale here. Starting point, this is going to be 0.145. 145 lambda. Just move towards the generator. 0.145 plus 0.1, which is 0.245. Now come to the point 0.245. Now this point. Now join this point with the VSWR circle. Just you have to draw the VSWR circle here, taking the radius of this. You have to draw the VSWR circle and look at the figure at which point the line intersect the VSWR circle. At which point line intersect the VSWR circle. So this point you will get the input impedance. See, this is 1.6 and this is 1.8. So it might be 1.65 in around. Okay. And what is the value of the X figure? This is the X. This one X. Maybe this one. This point. This might be X. So 1.65 and 0.1. So that is the value of input impedance. By this way, you can calculate the input impedance. Okay, and here is the angle of reflection coefficient. Angle of transmission coefficient. Let's see. A reflection coefficient in the input. That is, and the difference is in the angle. Now see one thing, to find out the actual value, you have to multiply it with the characteristic impedance. The value of the characteristic impedance was 50 ohm. So you have to multiply it with this one. Then you will get the input impedance. Okay. So that is a problem. I think you have understood it. Now look at here. Another one, another problem. So quarter wavelength. Lambda. Quarter wavelength means 0.25 lambda. Then what would be the input impedance value? Add this one 0.145 plus 0.25. Then you get the 0.395 lambda. So go to the 0.395. This is the 0.395 lambda. Join it, and from the center to the outside scale, join this one. Then you will get the Zin value. Here it has been found that is 0.8. How it is 0.8, 0.6, 0.5. Okay, see here 0.8. So this one, this is 0.8, and here maybe minus 0.4, around 0.4. This is minus. Why minus? Because it is in the lower part, the capacity part. This capacitive reactance. That's why it is minus. So multiply it. Then we will get the value. Okay. So how you get the admittance? Z0 is equal to square root of Zin into ZL. Okay. So if it is 1, Y1, normalized value. Because Z0 by Z0, if you divide it by Z0, then you get the normalized value of Zin and ZL. So Zin is square root 1 square Zin ZL, or the Zin is equal to 1 over ZL. So that is why just inverse it. 1 over ZL bar. Then you get this one. YL 1 over ZL. Y is equal to 1 over ZL actually. So normalized value of ZL. What is the normalized value? You have got the normalized value previously. Then just calculate it. Then you will get the result. Admittance. Okay. So today I have a plan to complete up to this one. Okay, so today we have seen the Smith chart and how to calculate the problems. Okay, so your task is to do these things at your home. Okay, the Smith chart things. Try to complete it. Try to complete these things at your home.